Hello, good evening to all of you, and good afternoon to our guest speaker, Professor A.P.D. Silva. So I warmly welcome all the participants and the guest speaker today, Professor A.P.D. Silva, who joined via Zoom to the fourth Inspire webinar conducted by the Department of Chemistry, University of Peradeniya. It's a great honor and pleasure to introduce our guest speaker today, a world-renowned Sri Lankan scientist, Professor A.P.D. Silva. Today, he is going to talk on fluorescent sensing and logic systems. He is going to share his expertise and insights into fascinating inventions he made. He became world famous due to his great inventions made using molecular logic and computation. His influential work includes the invention of molecular logic gates and the construction of photo-induced electron transfer, in short, PET sensory systems. So this world-renowned scientist, Professor A.P.D. Silva, earned his BSc honors degree in chemistry from the University of Colombo and PhD from the Queen's University in Belfast, Northern Ireland. He is a professor of organic chemistry in the School of Chemistry and Chemical Engineering in the Queen's University, Belfast, in the Northern Ireland. That is the university from where he got his PhD. He has over 130 publications and nearly 20,000 citations to his credit. His high H index of 62 reflects the high quality of his research work. Professor A.P.D. Silva is doing very interesting research in photochemistry. His work on fluorescent sensors has developed into a range of blood gas and electrolyte analyzers, currently sold by many companies such as Prof, Medical for human health, and IDEX for animal use, have surpassed 530 million US dollars and saved countless lives. Experimental field of molecular logic gates is another influential invention of Professor A.P.D. Silva. It produced a world record in terms of miniaturization of a computational act. There are so many other very important breakthrough inventions he made time to time. Some of them are construction of the first fluorescent sensor, the first phosphorescent sensor, the lanthanide complexes whose luminescence spectra are ion switchable. Molecular fluorescent PET sensors are some of them. Professor A.P.D. Silva has so many public outreach and key achievements. He received so many awards for his outstanding research output. The most recent one is Boyle-Higgins Gold Medal awarded by the Institute of Chemistry Ireland in 2020. Then in 2012, the first international award for molecular sensors and molecular logic gates. Also, he was awarded Royal Society of Chemistry Sensors Award in 2008. Those are only 3 of them. He is doing amazing inventions using molecules. So we are grateful to you for accepting our invitation and agreeing to share your expertise with us. I hope all of our participants get an enjoyable and unique experience in participating in this webinar today. Without taking much of your time, I cordially invite Professor A.P.D. Silva to start the webinar. Have a pleasant evening. It's over to you, Professor A.P.D. Silva.
Yeah, okay. Maybe you can't see my screen yet. Let me see. Can you see my screen?
Yes, sir, we can see your screen and also your video.
Okay. Then I'll slowly start. Oh, thank you very, very much. Thank you very, very much, Chandani, for this chance to share a bit of time with all of us together. So I want to thank all of you for putting aside some time so that we can discuss a few things that started in Sri Lanka. So I think that is the big happiness for me, really. And also, thank you very much, Melanie, for doing all the technology, because I am a very old guy and I'm not used to this technology at all. And also, I must specially say thank you to Manavadevi Ganhenage for sending an official invitation. So it was nice to get a very posh official invitation. But I think I must specially say Peradeniya has a special place in my heart because, as you know yourselves, you have a very lovely campus, a very beautiful campus, and you have lovely people. And I have been very lucky to know many of them. And I'm really glad many of them over the years, and some of them are here today. So I'm very thankful that Veranja was able to join all the way from the other side of the world. So thank you very much for sparing some of your time. And also, I want to really encourage the youngest among you. I hope I can show some of the little stories that started happening to me when, I suppose, when I was younger than you are. Some of the beginnings for me happened in school days, and then, of course, in the University of Colombo. So thanks to all of you. And another thing I want to thank you all for is that Peradeniya had a reputation and a continuing record of science research. We admired your research capabilities when we were in Colombo. So long may that continue. And I hope again the little stories that I will tell today will encourage you in continuing in that way of doing research in a very lovely environment and then producing lovely research for the whole world to see. So, with that kind of starting point, please allow me to address, if I can, what is on the screen here. Let me. So, the first word of my title is fluorescent. And as you know, fluorescent is where a molecule or a material takes light from the outside, input light, and then produces some light which goes away from the molecule. So light input, light output, and that would be a fluorescent material. Of course, we have fluorescent lights in the house, and so it's a very common phenomenon. And the most important thing about fluorescence, I would like to point out to myself and to you also, is that even though molecules are very, very small, so they are like a ghost, we can't see them. But when they give out a light signal, we know they are there. So it's a bit like a ghost. You can eventually get the ghost to do something, like Anjanam Balanava in the old days. And so molecules suddenly become alive when we can get signals from them. And fluorescence is a way of doing that. The second word in the title is sensing. And sensing again can be related to human experience. The official word sensing would mean sensitive to the environment. But the human meaning is far stronger, I think. We all have sensors, like we can see with our eyes, thank God, and we can hear with our ears. And these are our bodyguards. These protect us in our everyday living. If I was walking down the road and if I couldn't see and if I couldn't hear, a bus would come towards me and I would not see it. And if it's a Langama bus, then you never know. The bus hits me and I'm dead. No Inspire seminar. So, as you see, sensing is a matter of life or death. It's a survival thing for all living things. So, that's why it's a very human thing, you could say. And similarly, the fourth word in the title, which is the word logic. And as you can see, logic again, one of the official meanings of logic in a dictionary would be any stepwise process, anything you do one small step at a time. But again, I like to show you the human example of logic. Logic is where we explain ourselves to other people. So if we are having a chat, you and I, like I'm trying to do now, there is an idea in my head, and then I say some words, you hear the words, and it goes into your head, and you understand. And I don't mean that as a teacher, I mean that or as a student myself, I'm still learning all the time. I say that as a human being who has a conversation. When you talk to anyone, you are transferring ideas from yourself to that person. And then when you listen to that person transfers ideas to you. So it's like double brain surgery. One person has idea in their brain, you take it out, and then you put it into the other person's head, and that person then has the idea. It's magic, huh? But how does it happen? It happens with words, and it happens with words spoken in a logical fashion, stepwise. If the words are spoken slowly and the words transfer the meaning slowly, then we understand, and that is the meaning of logic again. So for intelligent conversation, we need logic. And if we don't have logic, we stop being intelligent. And we can't communicate intelligently to other people. So sensing is a survival thing, logic is an intelligence thing, or the higher level of survival, you could say. And just to mention, there are people who don't use logic and still convey ideas. And those are people who are called poets. They write a poem. We read the poem and we don't understand it for a long time. And later you say, oh, is that what the guy said? So what I wanted to point out to you there is sensing and logic are both connected with human information. How information transfers from like the Langama bus coming at me or something else, somebody else says to me, these are all part of how humans handle information of some kind and allows them to live and live well, hopefully, intelligently. And the last word in the title is systems. Again, as you know, systems would have a general meaning of a combination of parts which acts together to do something new. And when I say that, you will immediately say, I've heard of fluorescence in the technology things of today, like the light that comes out from your phone, from your computer screen, hopefully when you're watching this, that is a kind of fluorescence from within, or at least a luminescence from within. And sensing or sensors will be in a car, sensors will be in the house, in like some of the new fridges, if you have one. I don't have one. And or logic similarly will be in your phone or your computer, because logic devices operate your phone. And systems is a very common word used in computer engineering. Do you notice something? And again, I noticed this very late in my life, which is all the words that we referred to are now largely belonging in computer science and engineering, or what we call information technology now. But as I also tried to point out to you, all the words had a relationship with molecules, and we as humans are made up out of molecules and not out of silicon. Humans are very different in many ways compared to the modern information technology revolution, which of course has changed all our lives. And so it has had a great impact on human society. But the message I want to tell you straight away is that the new information technology, which gives us phones and computers, is very valuable, and it will help our lives to become easier and better, and maybe even save our lives at some times. But as I said, what I want to really impress upon myself and to you is the really important information technology is you or me. We are an information technology. Why? Because technology is the application or use of knowledge as a science. And what better application is there for a use of knowledge than me surviving the Langama bus for myself, or for you or for anyone else. And as I pointed out, sensing and logic are things that happen to us all the time, and we succeed. And therefore, that is the most usefulness that we can imagine for knowledge that there is. At least humans would think so, because it allows humans to survive and prosper. Bottom line of what I told you is there are two information technologies. One is the information technology based on silicon. The other is the information technology based on carbon. And the information technology based on carbon has existed as long as life has existed. We tend to think technologies are things you can buy in a shop. We have to be thankful that you can't buy people in a shop. Once upon a time, they could do that. But just because you can't buy something doesn't mean that is not a technology. The definition of a technology is not commerce, it is usefulness. And there is no better usefulness to humans than survival and prosperity. So that's a message I wanted to get across to you very early on, with very little science and maybe even more politics, but there it is. So that is what we are discussing. We are discussing how molecules can be made to use information on the behalf of whom? Of people like you and people like me. And I'm very lucky, very fortunate that couple of those things happen to be by accident. And again, I must quickly tell you, you know the most sophisticated word for happy accident, don't you? It is serendipity. Serendipity is officially the meaning of a happy accident, when somebody smiles at you on the road and you don't know that person at all. And that is a happy accident. Every time we survive, it's a happy accident. Because if there was an unhappy accident, I would be dead. Again, these are things I hope you will later discuss amongst your friends. It doesn't matter who you are. And I say this very clearly. It doesn't matter whether you're as old as me or whether you're really, really young. These are things that all of us as humans can talk about on an equal basis. And you can then talk this with your grandmother in your home. And I mean it with all respect. And she will understand this better than me. And so the bottom line out of what I'm hoping to show you is that if we take molecules which can communicate with us through something like fluorescence, then they will gather information for us and they will do step-by-step analysis or processing of something, which is what logic is also famous for. Like when I tell a sentence, then I process it in my brain and put it out in words to you. So that is the basis on which we can tell the stories on which this title was based. So if I now try to go on to my next slide here, this slide I'm very proud of, and I show this anywhere in the world I get the chance. And you can see why in the second line of the title, I'm showing you a word which is familiar to all Sri Lankans. So there is Colombo. I apologize, it can't be Peradeniya because I was not lucky enough to be there. So it was in Colombo that some of these ideas were discovered, and I'm very, very grateful for it happening there. And another point I make to audiences in many places is that not only was this work started in Colombo, which is, as we know, we are a small but great country, but emphasis on small in terms of numbers, in terms of land area, in terms of influence in the world, we are a small country. We have to face that. But still, good things can happen. And I also want to point out, just like in a place in space, it was Sri Lanka and Colombo. But the place in time then was in the middle of the 1980s, when Sri Lanka had a massive civil war and 100,000 people died. And some of them who I know and who you will know. So it was again to point out to people that ideas can grow out of anywhere. And so this is something that happened, and I would consider that true serendipity. So I was very fortunate to be close to a coconut tree in the 1980s, and just depending on the background that I had until then and the circumstances I faced then, this happened, what's on this slide. It's a way by which we can talk with molecules. Now, you might say that's something really mad, but we can communicate with molecules. As I showed you in the title slide, the moment a molecule gives out a light signal, we can see it. And the moment we shine some light towards where the molecules are, we might not be able to see the individual guy, but when we shine the light, the molecule will absorb that light. And then the process of fluorescence can begin. So now the question is, and that is what we are discussing in this slide, is how do we make fluorescence talk to us? The beginning of talking is to break up sound. If you just make a sound continuously, then you're like starting to sing. But in talking, we break the sound up. And so that they become small sounds, they become syllables, and then they become words. And then if we are clever, they can be poems. So that is what we are discussing in this slide. What we are discussing in this slide is how to take a fluorescent signal from a molecule and then break it on command. And the commanding person is you or me. So to start to get fluorescence, then what do? We take a fluorescent molecule or a lot of molecules, because usually we can't handle a single molecule easily, though there are lots of people in the world who can now handle one molecule. But for me, I'm still a poor guy here, and we take lots of molecules, put them into a flask, and then cook the molecule and connect it to other things. And that is synthetic organic chemistry on a small scale. So we take a fluorescent dye, the fluorescence which is on materials you will see. Some people, when they play sports, they will wear a t-shirt, and that t-shirt will be very bright yellow, for example. And that is a fluorophore, and here is a fluorophore. So no molecular structures, it's just a box. We are thinking in general ideas of philosophies. And again, I want to remind you, which is something I tell many people in different countries, is that Sri Lanka has a very rich tradition of philosophy and old religion. And then through that, we have learned a lot of old philosophies and how to think about things. And this is very powerful, because not every country believes in philosophy and education from a very young age. And in Sri Lanka, we were blessed with this and still are. And so here is a fluorophore just shown as a box. Later, we will put molecular structures to it. And now our goal is to change its normal behavior. So the normal behavior of a fluorophore is, if you shine light at it, which I'm showing with this broken purple arrow, that's a photon. One packet of light comes towards this molecule and is eaten by the fluorophore. It absorbs the light and the light is gone. But if a fluorophore was alone, then what it does is it eats it, keeps it for a while, and then says, I can't keep it anymore, and spits it out. That is fluorescence. But as you see in this case, I have shown the fluorophore as a gray box and no light comes out. Some of you have noticed it comes out here, but for the moment, I'm concentrating on the top half of this picture. Here is a fluorophore which should have given light out, but it has been stopped. Why has it been stopped? Because we have hijacked the energy of the light. Remember, when the photon comes in, it brings energy and deposits it inside the molecule. And then the molecule says, what can I do with this energy? And molecules look around trying to spend the energy, as we learn in school, actually, or first year university for sure. So the molecule looks around and says, I have lots of electrons inside me, and moving electrons is one way of using up energy. And again, we learned this from school. So very much Vidyalaya days, and we learned this, not Vishwavidyalaya, we learned it then, which is, if you push an electron from outside into the fluorophore, for example, that is a reduction. My school teacher, Mr. Errol Fernando, taught me this long time ago when I was 17. And I'm sure somebody taught you also at 17. An electron coming into a molecule or an atom is a reduction, and you have to pay an energy to do that. And that energy is the reduction potential. So there's an energy you have to give. So let's remember that. But now the fluorophore is not alone. We have connected the fluorophore to a red box, which is a spacer, which means it keeps the other box from coming too close. You can only look, you can't touch, like your parents will tell you when you're a teenager, kind of thing. After that, they say that's okay. So this electron arrived here from somewhere else, and that somewhere else is here, the green box. The green box that we have is a receptor. What is a receptor? The name means what it says. It receives other atoms and molecules. That's it. And biology is full of that, because our bodies and minds, like this moment, when you're watching the screen, hopefully, or having a cup of tea while you're listening to this, you are doing lots of actions to live. And those living actions involve a lot of receptors receiving a target of some kind. Your nerve signals depend on acetylcholine esterase acting on acetylcholine ester, for example. And I'm sure many of you will know much more biological chemistry than poor me. So there are many of these. So the moment you think, there are receptors catching a suitable target. So we have attached a receptor here, and we are pulling an electron out of the receptor. And again, Mr. Errol Fernando told me that when you pull the electron out, it's an oxidation. And the energy you have to give is the oxidation potential. So the oxidation potential on the receptor is a number we want. The reduction potential in the fluorophore is another number we want. And at that time, when we were in the University of Colombo, we could look in the library or go to another library, which is now the ITI, the Industrial Technology Institute, and they had a good library. Peradeniya always had a good library. And then we look in enough books and journals, and you can get these numbers for different fluorophores and different receptors. So by connecting these three boxes together, we have arranged for the fluorescence of the fluorophore to be killed off. It's dead now. Why? You hijacked it, as I said. And how did it happen? The photon energy, if you are careful, we can make sure it is bigger than the total energy you need to do the oxidation here and the reduction here. So do you see something? This was again something I enjoyed very much from that time till now. I like chemistry very much, but I think I like physics as much. And so this is where you can think like a physicist or like an engineer. And the molecular structure usually does not matter. So that was a big help when we were in Colombo at the time, because of course, unlike Peradeniya, our labs to do organic synthesis would not have been so good. So because of that, we tried to do minimum synthesis and tried to do more measurements where we could, like the physical chemistry part. So we could select a very simple fluorophore and a very simple spacer and a very simple receptor and combine them. But now, for not only for me, but for everyone around the world, they can choose fluorophores as they wish. Spacers, there are rules, of course, but the main rule we have discussed. You must know what the oxidation potential, the reduction potential, and the photon deposits the energy in the fluorophore. So the excited state energy, these three numbers you have to know. That's it. Of course, there are sophistications to this, which led to Nobel Prizes actually. But the basic idea is what I have told you. And now you and I are together in how we are thinking about this. This is one of the powers of this method. And I now feel part of the reason for that is because we found this method in the time of great crisis in Sri Lanka and personal difficulties as well for me at the time. And my grandmother was very ill at the time. And so there were many inspirations that came from that. And now here is this fluorophore spacer receptor system. And before I leave it, I want to also point out to you something else, which might be useful for those of you who enjoy thinking anyway. Receptors, as I told you, can come from biological chemistry or hard biology. It can come from molecular biology. It can come from physiology and various places like that. But similarly, the fluorophore can come from where? Not from biology. It will come from photochemistry or photophysics. Do you see something? The two parts of the molecule, the two terminal parts of the molecule are coming from different areas of science. This is very, very important. It is important because if you like thinking, Then if you like talking with other people and if you learn from other people, you can get your ideas from people who are very far apart. So you can get idea from physics, and I'll tell you a couple of stories about that later. And you can get idea from biology, or I found it very useful here for receptors to come from coordination chemistry. So like Professor Ramakrishna, who taught us in Colombo, I am very grateful for. I think I still use some of his ideas. And for the organic chemistry, we had Vincent Arkley, for example, who was a lovely, lovely teacher. And so now what I have explained to you is the fluorophore spacer receptor system. This is a system. Why? Because you take a fluorophore as a component and you combine it with other components, and then you change some property. And what is the change we have made? We have switched off the light signal. But that is only a part of it. If you want to develop words like in a conversation, then you must be able to switch it on command. Remember, we talked about making words. And to do that, we now have the bottom half of the slide. I'm sure many of you with very high IQ absorbed it already. But the argument, I hope I can also explain now, is very, very straightforward. And it uses cool ideas or first year university ideas. The same system, the fluorophore and the spacer and the receptor, but now the receptor has gone to work. What's its work? To catch a target. So it's caught a target. It's caught a metal ion. As I mentioned, I started this from like coordination chemistry background. So a metal ion was a good target. So when you catch a metal ion, you change not everything, you just change something. But the something is a very important something, because the moment you put a metal ion here, the electron finds it much harder to leave. Why? Aha, Mr. El Fernando taught me that, which is the electron is negative in charge, the metal ion is positive in charge, so they attract each other. So the metal ion talks to the electron like in a Hindi film and says, please don't go. That's it. So the metal ion holds back the electron, or if you like it in more sophisticated chemistry, the oxidation potential of the receptor goes to a higher number when the metal ion arrives. Now there are experiments done by people to show it, but a long time ago in the 1980s, there wasn't. But there was enough information in the journals to judge that, and we were very lucky with that. So now the receptor's oxidation potential is higher. So the price you have to pay is higher. So when you combine it with the reduction potential, which is nearly the same number, you add the two numbers together, the numbers are bigger now. No signs, just add the magnitudes. So now the photon energy deposited in the molecule, the excited state energy, is not big enough. So we can judge that when you're designing it. And so then the moment the metal ion comes in, the electron transfer stops. So as you remember, Chandani very kindly referred to photo-induced electron transfer. That is PET. That is PET here. I forgot to mention to you. PET, the photo-induced electron transfer, is what happens in every green leaf in lovely Peradeniya that you would see. The moment you see a green leaf, what's happening? The solar light that falls on the leaf, the green light is the only thing that escapes. The blue and the red are absorbed by the leaf. And what does the leaf do? It makes oxygen. Where does the oxygen go? It goes up your nose and it helps you to breathe. And what else does the leaf do? It makes starch, if it's rice and so on, or many other things. It makes starch and we eat that for lunch or for dinner. So that is our survival and prosperity again depends on PET. So PET is a very grand phenomenon, but we were very fortunate in Colombo at that time to show another usefulness of PET. PET was not discovered by us. It was discovered in Germany, actually, in Stuttgart, where Mercedes cars are made, for example. It was done in Stuttgart by a person called Weller in the late 1960s. But I was fortunate to be studying for a photochemistry PhD a little later in the late 1970s. And so this idea was very fashionable then. So it required that serendipity for me to realize, oh, here's something new, and maybe I can understand this. And then when I was back in Colombo looking after my Archie, I think it was a time where there was plenty of time to think and then imagine things. because that's all we could do. There were many problems in Sri Lanka at the time. Some of you older people will remember. So it was a great time to think, and this idea came out of it. So I'm sure if there was no problems at that time, and if I was in another situation, I would not have had the time to think. So I feel grateful that somehow some good came out of a hard time. And so there we have it. Photo-induced electron transfer, which is so important in agriculture generally, is something that we can use in photochemistry for healthcare, as I'll show you. And what does it do really at a philosophical level? It takes a ghost called a molecule and it makes the molecule talk to us, because we can tell it when to say something, when not to say something. So that's the idea. So this is the way by which we can get a molecule to talk to us with a light signal. Don't forget again, and I'm not forgetting it also, this light signal hits my face. The molecule is really small, I'm really big, but we talk to each other now. And what does this light signal tell me? The receptor has caught a metal ion of the chosen type. So if you make a receptor selective to a particular metal ion, then you can count those metal ions. Now we can do analytical chemistry or analytical science in general. We can do analytical biochemistry or analytical physiology actually now. So now let me take you to the next slide then. This is just a picture which demonstrates how well this effect works as a visual thing. Like I have shown this to primary school children in the days when we had no viruses and we could travel, and the children just go, wow. And some of these children were Sri Lankan. We used to go out to faraway schools through the popularization of science committee. And then you just show this to children and they go, whoa. And so there it is. So here is a beaker which contains some of these fluorophore spacer receptor systems. Here is a beaker of the same sample, half of it, and into it we have added the target metal ion. And all these beakers are being illuminated with the ultraviolet light, like you have in banks to check whether a check is good, for example, or which are used in the lovely research labs that you have for looking at TLC plates, for example. And you see here, there is no light. It's like the night, but here blue light all over your face. And you can then design a molecule with another fluorophore and check for these oxidation potentials and reductions and the excited state energies, and then you can signal it in green or red. And if you can do RGB like on your phone, you can make any colors by mixing them. And similarly, you can do it the opposite way. You can design it, so it's very engineering system. You can design it so that initially there is no PET, and then when the target arrives, a PET happens in the opposite direction, for example. And also there's a nice thing here for computer science people who are interested in computer science, and I am interested very much also, is that these are what in computer science is called a yes logic gate, meaning when the input metal ion is low, the output light signal is clearly low. There's no blue light here, almost none. But here, when the input metal ion level is high, the blue light output is clearly high. So the input and output follow each other. So the output says yes to the input. That's why it's called a yes logic gate. And then you have not logic gates, and that's the one here. Not logic gate is where the output opposes the input. Like many of you in larger families will know this. Younger brothers or younger sisters will usually try to give the elder brother or elder sister a heart attack and disagree as much as they can. But they really love you all the same. So in this way, we can see how this light signal change can be useful not only in chemistry or general analytical life science, but it can also have a relationship to computer science as well. So now I want to show you a map, and I show this map in many places, and I try to show them where Sri Lanka is, and to show them again that though we are small, we are certainly in the middle of an ocean, and that brings its good side and its bad sides as well. But this map is mainly also to show people that a little idea that started off, well, I must say, the idea didn't actually start off in Sri Lanka. When we did it in Sri Lanka in the 1980s, I thought we were. But then when we slowly made the first publications, then people wrote to us and said, hold on here, you are not the first guy, because my literature searching wasn't good enough. I think we may be number 4 or number 5 to discover the basic idea, but to show that the idea is general, we were the first. So we showed that it's not a one-off thing. So the 4 people beforehand did one, or one person did 2 cases and then stopped. But we just kept going, like the hare and the tortoise story. We were the tortoise. We just kept going, the small libba. We kept going. And we showed that it's a very general principle. And that general principle is what I shared with you in the previous slide. And this map is again to show you how because the idea is nice and simple. Like, remember, in science, we like to say an idea is simple, but here I will claim that it is genuinely simple because the ideas come from what was taught to me in school. That's why, if I take that as a definition. And also, I would offer these maps as a proof of its simplicity. There are lots of people. This is only one map. There are several other maps and over 925 labs that I have counted one by one, people who have published on it. And there are people who are very, very lovely people. Like, I must mention, like, up at the very top of this slide, there's Grigg towards the middle there. And Professor Grigg is the one who gave me the job in Belfast. So he died last year. So I would very much like to remember him at a time like this. But then there are lots of others, like the name directly below him, Stoddart, has been like a big brother to me and helped me a lot to get started in the profession of chemistry. And of course, as many of you will know, like, he got a Nobel Prize in 2016. But these people also found that they could use this simple method because it is simple. And then people want to measure all kinds of things, metal ions all across the periodic table. And sometimes you want to measure anions, sometimes you want to measure neutral things. And of course, there are molecules and molecules and molecules. And so this method has slowly been generalized. So that's why there is over 900 labs doing it now. And so here is another map. If you didn't find your favorite chemist, then you might find the person here, or somebody you worked with when you did your PhD in America or Japan or like that. And so there are various. And it's also a way of seeing where in the world where they take science very seriously. So you are seeing countries where they want to analyze, like, for example, some of our good friends in China, like, they want to measure mercury, which goes into water because of rapid industrialization. And then they build PET sensors for a G2+. And then they measure it in rivers all over the place across China. So now I want to tell you a very particular story. But again, I want to tell you this particular story for several reasons. Maybe the place to start is that during the really difficult times in Sri Lanka, during the war, during the civil wars that we had, if I remember right, it was in about 2000 and maybe 2001 or 2000 was when some of these people from this giant multinational, Roche, like, you can go to a local Osusala and you can see this blue diamond because they are such a massive, massive company, and they manufacture all kinds of medicines, but they also have a diagnostics division. So their diagnostics people happened to read a little paper that we had written. I used to think it's only my mother reads my papers because she loves her son. But thankfully, on that occasion, serendipity again, Roche were trying to develop analysis of blood, and they had ways to measure pH, for example, but they couldn't measure sodium reliably. So they were desperate. They had half a product and they couldn't make the full product. And then they read this journal, and I'm very fortunate that they did. And then they came to Belfast. Like, if I tried to go to Roche in Switzerland, they would have put the dogs on me. They would say, "Who are you?" So they came to us and wearing their Armani suits, and we said, come in. And what do you want from us? And we were very grateful. And of course, then we had a lovely collaboration, and I'm very, very grateful because we just had a simple enough idea. And I used to just dream sitting under the Tambili tree, small Tambili tree, where I lived near Colombo, would think, like, how nice if we could measure the potassium content inside a Tambili while it's growing. And just imagination, like, someday can you measure it in people? But that's all. I never seriously thought I could do that because I am not really a doer in that sense. I'm just happy to think things, and that's it. And maybe science suits me for that reason too. But then the people in Roche, they are doers. They want to do things. And then they challenged us. So they really challenged us. And of course, they said, now you have to make it work. We are going to have faith in you and you have to repay the faith. And so I'm very fortunate, serendipity again, I suppose, we had the method, like what I told you, oxidation, reduction, potentials. And they said, right, yeah, we want to measure sodium in blood. And then they told me what the concentration of sodium in blood is. Now, I don't know my biology, so I didn't even know that. Now, many of you would have known that from school, from biology in school. They just photocopied in the old days, a page from a physiology textbook and sent it to me. Sodium, 0.1 molar, roughly. So that's what you had to measure. And so I was claiming our method is a nice engineering principle. We can predict, and sure enough, we had published several papers by then to show it's predictable. But now they were saying, right, now there is money on the line, make this work. And our university encouraged me, but finally our university was not efficient to deal with Roche. So finally it was poor me, and I can't deal with them. I just said, well, I'll try to help. And they said, of course, now you have to. And so they said, let's go. Let's make a sodium sensor to measure sodium in blood. Of course, they knew tricks which I didn't know, which of course they later told me. Blood, the only thing I knew was it's very red. So you can tell the amount of biology I know. So I said, if it's red, I can't measure in it. They said, leave it to us. What do? They filter the blood. They filter it through a micron filter paper. That's all. And then you get the serum of the blood. The serum is colorless, basically. So a blue LED is what you use to shine light at it. So this was in the late 1990s. So blue LEDs were quite precious at the time. But with a blue LED, you wanted to shine light. So we found a fluorophore in the literature from the books, no problem. BASF make this as a commodity chemical. And you can recognize this as a fluorophore. Any one of you and me can recognize it because it's got a lot of double, single, double bonds. Conjugated pi system, which we learn for first year university or maybe in school. And a very flat aromatic molecule, and these are usually fluorescent. So that's it. And this one absorbs blue light. So that we checked. So then it emits like a yellowy green light. So there we have our fluorophore. So now we needed a receptor to catch 0.1 molar sodium in water. So we looked around in the journals, and luckily a friend of mine, it so happened in Missouri in the USA, had made this piece in the green. It's a crown ether, nitrogen and 4 oxygens is called an ASA crown ether. And he had built this and measured the binding constant for sodium in water. And he measured it and he found it was 10 units, 10 molar minus 1. So if you take a binding constant of a receptor and you take the 1 over number of that gives you the effective concentration where the sensor will catch it. That's it. Physiologists know this really well. Chemists didn't use it all the time, but there it was. So we got the right molecule with the right binding constant for sodium and potassium very well. And in many of you will know in blood, the potassium level in blood is quite low. So it was quite easy to select for sodium. Make the molecule and connect it onto the filter paper. And then this works. Now I say it like that. At the time, I was a bit nervous, but we had a lot of confidence that it will work. So there is the most precious story I wanted to tell you. And I must tell you the connection with Sri Lanka. The Sri Lanka connection was a few years after this started to be sold. This was bought in Sri Lanka. It was bought in Sri Lanka. Why? And this is what Roche told me, but some of you may have actually seen this. At that time, we had a lot of suicide bombings, sadly. And so then there were lots of injuries beside deaths. And so when a person is injured from a bombing, then you need to test their blood immediately and take them to the hospital and give them the correct transfusion. The problem with the transfusion was the salt level. When we normally have blood in the blood bank, they don't measure the salt levels. They just give the right blood type if they can. But in a hurry, then they give type O and that's you. But the type O person may be a high sodium person. Now they check from the blood bank when they issue the blood, say if it's needed for me, they check my blood and check whether I'm high sodium or low sodium, and then give me the correct type O blood. If I am high sodium, they give me high sodium transfusion. Otherwise, those people who were, the surgeons do their business, they do their best job, and they try to save the life, but the patient dies in post-operative care. Why? Because the high sodium and the low sodium bloods mix, and then you get salt shock. That was it. So those lives were all saved from the time this was used. And there must be many people in Sri Lanka whose lives are saved now because of this, not only Sri Lanka, but around the world now. So this is a lovely, lovely story, and I hope you share in the loveliness and the happiness of it, and to remember that it happened in Serendip. It very much happened in Sri Lanka. The beginnings of the idea all happened there. And here is something you can again share with your grandmother or someone. When you go and chat with them later, take your phone with them, with you, and put OptiMedical into your phone. And when you put optical medical into your phone, then you will get Opti products, and show that to your grandmother and talk about it. And similarly, if you want to go to idex.com, it's a big site. Actually, they own OptiMedical now. They have lots of veterinary products, but inside, if you look for VetStat, you will see this again. And this product is what is on this slide. And I'm very happy to show you it. And here is one in my hand. You can see it's very tiny. It's about maybe 4 centimeters long. That is all. Little piece of plastic. And this red portion comes off, and then you can put some blood into it. And so people in those a suicide bomb site, the paramedic will come there, God bless them, they come and they take a little bit of blood from an undamaged part of the person and put it into this little plastic chip. And in 30 seconds, once you put it into this box, it will give the numbers of your sodium, most importantly. And as Chandani kindly mentioned, this has made quite a bit of cash now for Roche. Our university was not clever enough to get a good deal. But again, I think the cash is not the important one. It's a huge amount of money. It's over $500 million US now. And it's more than that now. Now, Roche and I don't have a formal connection anymore, so they don't tell me what the balance sheets are. But it's a huge number now, and it's off patent. So lots of other companies, or several other companies, manufacture it as well. But the most important thing I want to say to you is the human value of it. Like, it has saved lives, as Chandani pointed out. And I'm very grateful to discuss it with you and to say that it happened under a Tambili tree in Colombo. So there. So these are the things that helped me, and I hope it will help the very youngest one of you. And if you are thinking of whether chemistry can be useful, here is an example where chemistry is useful. And it started with A-level ideas from Sri Lanka. That's what it was. So in the little bit of time I have left, if I may, like for 10 minutes, let me share with you maybe the more, I suppose, the lasting scientific contribution that I was lucky to make. And even here, serendipity played a very large role. I am a slow moving person, like I mentioned, like a tortoise. And so for me, it takes time. And here, like, first of all, to say, here is, I think, one of the genius of geniuses in the world. He is called George Boole. And I would take as the definition of genius, if his idea is in your pocket now. So even Einstein wouldn't qualify under that definition. In your pocket will be some money and various other things, maybe a photograph of your girlfriend, boyfriend, etc. But you will have your phone. And this guy helped your phone to happen. Without him, the phone would not have happened. The mobile phone certainly would not have happened. George Boole is the guy who showed that language can be made into mathematics. He was a mathematician, and he worked in the south of Ireland. And he worked in the south of Ireland at a time of a huge shortage of food, and over 1 million people died. They believe now the population of Ireland would have been the size of the population of Sri Lanka, 20 some million. Now it's 4.5 million, that is all. And the influence of the famine at that time, 1850 or so. George Boole worked there at that time. So again, in a moment of heavy crisis, and he made this discovery, and then his students developed it further, and then it became the logic gates, which are inside your phone. There it is. So then maybe because I'm Sri Lankan, and also I still have this fate feeling somewhere. And I think then it was a matter of fate that here is some huge discovery. And then we made a small discovery in the north of Ireland much, much later. It was a small discovery, really. What he made is truly world-changing. But ours, we hope it'll influence chemistry at least as time goes on. And Nimal, who's from Sri Lanka, he's from Vattala, Nimal Gunratna, and Colin, they are both still working independently at Queen's now. So we have been great friends, and it's been great to watch this happen from the start. And so we were able to show the first molecules which could do logic. Again, be one of the first to think that molecules can do logic. Lots of people had thought about that, especially some biologists had thought about it. Like, how do humans work? And they had thought, can it be related to this new thing called a computer, which seriously started happening in the 1950s. So they had thought about ideas like this. But in this case, as far as we can track, we are the first where we showed that molecules in a lab can be made and designed to practically perform logic operations and small computations. And again, thanks to Chandani for pointing out a couple of those things that happened subsequently. And so in the years since then, and so when about 20 years had gone by, I eventually collected all the ideas from not only me, but many other people around the world. Many friendships formed out of this. And I put it into a book and called Molecular Logic-Based Computation, collected all the ideas that are present and the cases that are present. And then, of course, I was very grateful to good friends in China and good friends in Japan who translated the book within a year into their mother languages. And of course, I asked them, why do you want to do this? And they told me something very, very important. Both of them were saying, we want our young people to learn ideas in the mother language. I'm very grateful for that. In Sri Lanka, I learned some and I went to a mixed school. And so I'm very grateful for the language and the culture experiences that I've had. And here I was very grateful that in these two countries, which place a really high value on science, decided to translate the book first thing, so that then young people would read it and think about the ideas inside. So I'm very happy that it happened. And of course, many other things have happened in these rainbow arrows I'm trying to show you. Like in 2000, we showed the first molecules which could count, like a baby will count. And to count just small things like what is 1 and 1, and that's it. Like, and now it's gone a little further. Now there are molecules which can play games, like tic-tac-toe, which we play as children. Now those can be played with molecules. We didn't do that though. People in Columbia School of Medicine, some people did it there. But just to finish off, let me work down in the next 5 minutes or so. I want to show you a human level computation, meaning molecules can do what you do. Now, this again, some of you say, no chance. No, I'll show you. Because the human value was important throughout this little talk, and I tried to connect with that as often as I could. Like the little blood analyzer is for human use and animals, of course, but it connects with human life. So chemistry is a very human connected subject. And the fact that we are made out of molecules adds to that. And so we can contribute a lot towards the well-being of the world. And the roast chip will certainly do that. And there is room for more. And I would point out again, if it can happen to a slow guy like myself, who was present in times of crisis, I tried to show you how that was an advantage for me in some ways. I'm sure it was damaging in other ways to me and many other people in Sri Lanka at the time. Some died, of course. And so for some of you now who are really young, who don't have that kind of major crisis, hopefully, and then what more can you do with your high IQ? So I hope genuinely in that way that it will inspire, as these lecture series are so thoughtfully called. So here is my lead up to the human level computation in maybe 5 minutes, if that's okay. And so this picture is just to first show something from inside your phone. If you've been unfortunate at some time to break your phone and or your smartphone, and if the pieces fell on the floor, or you threw it on the floor, and then you need to eat a bit of kohila and things. But then if you saw the broken pieces inside, then you would have seen the logic chip. The logic chip is usually a black square, and it has golden colored legs like a spider. And so it receives inputs along the wires, and it puts the output out through the wire. That's it. So that's the logic device. Now I want to show you something from one of your lovely labs in Peradeniya. You take a test tube, and into the test tube you put a substance, maybe an ester, and then you pour sodium hydroxide into it as a reagent. Then you heat it. And then after a little while, the ester, which is an oil, will change into clear liquid, And then later you will add a bit of acid, and then you will get a white precipitate. And so you can see it. You see the readout. Did you see? The philosophy behind these two orange colored squares is the same. Input output systems, that's what they are. Or if you like to think more in civil engineering, action reaction, that's what these are. So the moment you have that philosophical connection, then suddenly chemistry can do what computer science does. And as Cosette pointed out to you, our bodies is doing that all the time. It may not always use Boolean logic, but it does input output operations all the time. That is, the logic device only uses voltage in, voltage out. And that enabled the information technology revolution to succeed a lot, because then you can join one logic device to another, to another, to another. Life doesn't work like that. Life is very diverse. So it can use sodium hydroxide coming in, heat coming in, and a white light coming out. So that diversity can be exploited in chemistry, and these are examples from the literature of logic devices which have used atoms or molecule ions as a reagent coming into a small supermolecule, like the Roche sodium sensor I showed you. And then conditions can be like temperature or a voltage. And our early cases were based on fluorescence, like the Roche chip, but lots of other things have been done since. This slide has not been updated since 2013, I apologize. So there are many more cases now. But now again, there are lots of world maps. Now we have 1,200 labs which I can identify, not only chemistry labs, there are maybe nearly half molecular biology labs now. DNA has become a great vehicle for molecular logic now. So it's wonderful, wonderful. So there are genetics labs here. There are computer science labs here who do wet labs in computer science. And their colleagues are frightened of them. So because they are dry labs all the time with computers only. These guys mix liquids and things. So it's a wonderful, wonderful subject. And as you can see, these are very crowded maps. And now here's more names. And again, you might see some scientists who you like in different countries. Here is another, well, I've only shown you two. Oops. There's a third map which I was trying to fill up, but I'm glad I did show it now. So here's my last example. And thank you very much for your patience. And thank you very much for your engagement. And thank you very much for the chance for me to get into a situation where we share some time together. Here's my example. I promised you an example of where is this molecular logic connecting to humans. Here is a human connection. The title says edge detection. Edge detection is very, very common. For example, if you're on Zoom now, Zoom will allow you to change your background. And so you may be sitting at home, but you can pretend you're sitting in lovely Peradeniya gardens and you can put a picture behind. How does Zoom do that? Or many other devices will do that. Software devices will do that. And they will do that by edge detection. They will draw the edge of your face and your head. They draw the outline. And then everything outside your outline is changed into lovely Peradeniya gardens. That's it. So that's edge detection. It's done in Photoshop and it's done with many other information technology places. Machine vision does it a lot in factories when they are producing things at speed. But the important one is here, animal vision. When you look at something, when you look at the screen now, if your eyes are open, then edge detection is happening. This is amazing. I was told this by psychology friends, and it's amazing. I'm really grateful to be able to talk to people who are outside our discipline and learn from. And I must say, I forgot to say it earlier, I must say it now. I am doing molecular logic really because of great inspiration from one guy. Veranja will know this guy. He's called Satish Namasiva. He's now at the University of Moratuwa, and he's a physicist, and I like physics, and he would teach me physics for fun. And one day he took me into a lab and showed me logic gates. This was way back in if I remember right, early 1980. And he showed me logic gates and then big logic gates. And he showed me what they could do. And I'm going, whoa, this is magic, but I don't know what to do with it. And he was showing how you can make clocks out of it and things. And then much, much later, because I'm very slow, and then thought, oh, can molecules do this? And luckily for us, then we were in the right place, right time, I suppose. And then it happened. And so in edge detection happens to you anytime. You have no control over this. This is very subconscious. You are checking whether things in front of you are dangerous or not. And so to do that, you draw the outline. So for example, I can show this to you through the little camera. Like, say, suppose you saw this edge, okay? I don't know whether it's clear in the small photo. I was showing me with huge ears and a very long nose. I was trying to pretend to be an elephant. My edge is very different then. And because the edge is different, and all Sri Lankan children will have a record of the edge of an elephant in their brains. Because we have seen elephants, and elephants are very different from people. And so when you see it, then you might say, oh, how huge is that? And then you draw yourself the outline and send it to your brain and say, watch out for the next time you see this. Because if you're not careful, the elephant will put his foot on top of your head, then I'll become a pizza. So just to avoid that, then the brain keeps a record. This can't be dangerous. So then what the eye does, and it does it in 1 millisecond, 1 millisecond. It takes a photo, draws the edge, like in Zoom, sends it to the shallow part of the brain and says, have you seen this before? And it sends it back and says, no, that image is not of an elephant. That is of Veranja Karunara. And it says, he's fine. And so we can chat. That's the idea. So notice it's very deep-seated human behavior. And so it's wonderful to do this with molecules. And so again, I'm very thankful to people like Jue here and Gaua, Jessica and Tom. So with them, we were able to develop this example. And there's a bit of chemistry here, but because I've already taken too much time, I'll just show you the experimental result. Oh, the experiment is this. You take a filter paper and you soak the filter paper in a mixture of molecules, which is our computing system. Then we take a mask, we cover the filter paper with a sheet of black plastic, but we cut a hole in it. So it's a square hole. Then we cover the paper and shine 254 nanometer light from your TLC lamp. This was a very cheap experiment. A short wave radiation from the UV lamp. And you shine lights for various amounts of time. Then after shining, you switch off the lamp, take off the mask. Then you take a photo of the paper looking for the fluorescence of the paper by shining long wave UV light from the same TLC lamp that you have, the next switch. So long wave light and take a photo. So you do it at the start, nothing to see, it meaning 0 time of 254 nanometer writing. Then you do it for half a minute, 1 minute, and we keep doubling. And you see, after about 8 minutes, you can clearly see the photograph, like an old-fashioned photograph in your grandmother's house. You will have a photograph of when she got married, maybe. This is a positive photo. Here is the object, here is the image. But that's after 8 minutes. But you wait for 32 minutes, see what happens. The inside is blue again. The outside was always blue. The border, like in a sari border, now you get about 1 millimeter thick here, an orange border. This is the visualized edge after detection. There it is. So here are a mixture of simple molecules, we can chat about it later if you like, which behave like you. Of course, it's not as clever as you because it can't do the other things that you do, which makes you interesting and loved by other people. That it can't do, it's just a filter paper with a few chemicals in it. But, and there's another failing, it takes half an hour to develop the edge. So the elephant has plenty of time to make a pizza out of AP. So that's it. So this is not very efficient at the moment and it can't save any lives. But the idea is there. And I'll just show you another slide and stop. This is one of the most famous line drawings in the world, done by Leonardo da Vinci. It's a line drawing, huh? Okay, it's a naked man, but it's a line drawing and his face is drawn so carefully. You should be able to recognize the guy if you lived at that time. Maybe this guy laughed at Leonardo once and he drew him without his trousers. Now, this universal man is a line drawing. There's no color, nothing. Line drawing happens from edge detection. In fact, I asked some artists and they explained to me that line drawing is their lowest level qualification for art. And line drawing is where you recognize the border between light and shade, and that is edge detection. And so here we did some cases for Ireland, for example. This is the national symbol of Ireland, the shamrock in green, for example. But you can do detailed things like birds' feathers. So thank you very much. So I tried to tell you a few stories about how molecules can handle information, especially for gathering information like sensors, which we saw can serve across the world. A very practical example, not because of me, but thanks to a big multinational who happened to get involved with us. But the idea started out in Sri Lanka, and I hope you celebrate that with me. And I hope you also celebrate the fact that it's not just a discovery, it is a discovery which brightens up people's lives, because some of those people would have been dead now if not for that product. But then I also tried to show you that the same ideas with a fluorophore and a spacer and a receptor can be converted into mathematics or converted into computer science. And there maybe is the bigger contribution, because a large part of us inside, in every single cell of ours, this kind of computing happens. And this is the beginnings where molecules can do these things. So thank you very, very much for your time. Thank you very, very much for your patience, because I went a little over time, but I think we'll be very happy to discuss. So over to you, Chandani and Melanie. I'll stop sharing the screen now, maybe, if I know how.
Thank you very much, sir.
My pleasure.
It was an excellent talk, and we all are excited with your talk. And again, thank you very much for your nice talk. I mean, we can see you are so fashionable about science. And
yes,
from this onwards, we would like to have little question and answer session. So I would like to invite few of from our audience to raise some questions. So you can use raise hand option available in the Zoom, so that we can conduct question and answer session very smoothly. So it's over to the audience.
Melanie, can we just ask the questions straight away from...
Are you born? Yes, yes.
All right. I'm Gamini.
Yes, yes. Lovely to see you. Lovely to see you.
It's a lovely talk. Actually, I was busy from 1 to 1 o'clock onwards, Matra University Selection Board. So they did at 5 o'clock. They stopped at 5:20.
Oh, but no problem.
So I joined from there. But still, I quote many of your wonderful presentations. Of course, I mean.
And congratulations for developing the breathing. You did the mask, isn't it? Congratulations.
Thank you, Henry. Thank you. So I have quite a few questions, actually. I mean, I'm sure some of these things are like, I'm always kind of mad. So you have been using UV and visible light, obviously for electronic excitations. But what I was thinking is that, I mean, in the night, we have enough IR. So IR cannot do any electronic excitations, but we know how to convert IR into UV and visible by photon up conversion.
Yes.
So can you couple this radiation and photon up conversion to work your devices?
Lovely idea, Gamini. Lovely. Actually, there are a few cases now where they apply this, not by me, I must say. They take the basic PET sensor system that I mentioned to you and transfer it, instead of using a fluorophore as a dye, by using a quantum dot and having an upconversion nanoparticle joining it. And so the method does work. Yes.
Yeah.
So they do it that way. And the other way, which is very successful in South Korea now, it's a Professor Park, but they have a lot of parks. So what they do is also, but then you need high power, short time lasers. You pump the dye so that it does a 2-photon excitation.
2-photon, yeah.
So the TPC also can be used. So at the moment, there are both these methods, but you're very right. So in the future, there can be bigger applications with upconversion, or even with the 2-photon excitation, especially for microscope experiments.
And also
so they have cell samples and you put the IR laser through the objective. Yeah, so great idea, not mad at all.
Another thing is about your last few slides, like I mean, that using that photo acid generator and things like that, quite common in lithography. So
exactly.
Have you not been copied from that lithography?
Oh yeah, in fact, that molecule, I found it in a IBM patent. IBM had the patents for cutting the chips on the phone. And so of course, they use it to cut the features on the silicon, We are using it on the filter paper to generate protons in the location we want. So you're right.
Yeah.
The idea is originally from physics there.
Lithography, yeah. It looks like that. Yeah.
Well done. Well done.
There are a few more questions, but I mean, I should leave this for others as well.
High quality as usual. Yeah, excellent.
Thank you, Evi. It's nice
Pleasure,
to meet you
Gavini.
after some time.
And I hope you have many sales with the mask.
Yeah, there's a quite good sale these days now, but we are waiting for NMRA approval. All the tests are passed, but this process is very slow.
Yes.
Taken more than 6 months now.
Yeah, those are difficulties
in
always.
In the abroad, for export market, we need to have this NMR.
Oh yes. So I wish you very good luck. Yeah, and congratulations.
But in the local sales is very good actually. So we are not doing it. The patent is owned by the university. Actually, I transferred patent rights to the university.
Okay.
And we are only inventors, and there's industry, and it's coupled with the state sector.
Yeah.
So ST, State Trading Corporation, is the official sort of
distributor. Yeah. Oh, I think you'll have good sales with it, I'm sure. Congratulations.
Thank you.
Thank you for your question, Rajpak sir. Silva sir, there is a question in the chat window. Watching LED TV is good or bad for the health? It's a general question. I hope you hear my question.
Yes. Oh, I think that's fair enough. Again, I may not be a good example to answer the question, but I can certainly try, because I don't watch a lot of television myself. But there is a part of it which I understood a long time ago, and I'm sure many others in the audience will know this also. Like in low-level light, if we are watching any screen, and if we watch a screen which is changing the picture rapidly, and especially I think games players, I think, go through this difficulty. Like they concentrate so hard, then their eyes get closer and closer to the screen until their nose bounces off the screen. And then you're so involved in it, you forget that your focal length of your eye has been made smaller and smaller. And of course, it's a big problem with smartphones, as you know. Of course, I'm an old guy, right? So I may be the bad guy to discuss about this. On phones, because the screen size is made to fit a pocket, the font size on the screen is 8, or sometimes even smaller. And 8 font size, like if you go to an optician and ask them to show you 8 font size scaled to what you read on their screen for glasses, everyone will need telescopes. So we are forced by technology, because it has to be convenient, so it's got to be small. But if it's got to be small, and if you don't keep swiping the screen too often, you have to fit all the characters on the screen. So see how technology drives human behavior. So there we have to learn to budget our time that we put on these things. So for example, like remember the common thing told to even a hospital patient is, if you're in a bed, if you are healthy enough to walk, you have to get up and walk every day. Otherwise the nurses will come and hit you and they make you walk. In the same way, if we are watching a screen and if we are taken up by the screen of whatever it may be a Hindi film you really love, Rajesh Khanna in full flow, and then you forget for 3 hours, you're stuck on the screen. All your muscles are not moving. Your eye muscles are not moving. They're strained position. So then naturally, I suppose we damage ourselves. So the problem seems to be multiple. I think it's again a conversation to be had with your family, friends. Like, should we watch however exciting the program you're watching is? After all, it's only a program on the television. Should we be able to switch off? Should we be able to go out and just enjoy the lovely environment in Peradeniya? Like, now these are things I suppose people can discuss in general. But as a science person who has been interested in optics all along, and I am half blind myself, so we can do that same damage with a book. And I damaged my eyes with books that way when I was a child. You keep reading and the sun goes down and you keep reading, and we didn't have electricity. And so you keep going in the dark because you're involved in the story. And so I'm half blind now. So I think it's a general message. And I suppose the message comes from old Buddhism, like middle way. Not too much, not too little. That's the best answer I can offer.
Okay, sir. Thank you very much for your explanation. Yeah, I think your very much good.
Can I ask?
Go ahead.
Make a little comment.
Of
Oh,
course.
go ahead, Ratnayaka, go ahead.
Yeah, okay. AP is really wonderful. It's a nice presentation. In fact, you are connecting at the beginning the scientific concepts with philosophy and day-to-day activities. That was excellent.
Thank you, sir.
I see, something else also there, that the entire thing is connected, kind of connection.
But I suppose it's true, Ratnaka, what you say, but I think you and I were brought up in that environment. And I suppose that's why I like you, you like me. We grew up together in that culture, which is where there was a lot of storytelling. I value that very much. And like, I am mixed religion background, as you know, but I was very lucky to spend time in a Peradeniya. And then during that time, the monks would laugh at me because I'm mixed religion, but they accepted me and they would teach me the methods of communication. And I still feel very grateful for that. Because as we know, like you would have known very well, like in science, sometimes it will be, you are told you have to drive it from an ego perspective, or you have to advertise. And I suppose I'm advertising in a kind of way, but I'm trying to remember that the message is to share a story. And in fact, you told me that a couple of days ago in your lovely email, is to tell a story. And I think we were trained that way. And I still feel grateful for that. And I share that with many audiences in different parts of the world. And I try to tell them that now I am a finished product of course, Ireland has formed a part of that, but a large part of it is Sri Lankan. And I'm very grateful. Like my Sia happened to be the only Sia I knew, was a school teacher. And so again, he had this attitude of teaching. And so I watched it all along. And I remembered the way in which he would, I suppose, be looked after by his community. And I'm sure, Ratnaka, you have a lot of relatives who were like that. And I think I then felt, yeah, I'd like to grow up to be like you. And one of those things still is to tell a story. And so I am very glad to discuss that with you, because I know you do the same.
Right. Thank you, AP. Thanks a lot.
Pleasure, my man. Pleasure.
All the best.
Yeah,
All the best to you,
yes, sir, as we are running out of time, we would like to have one more question. And there are so many appreciating comments for you, sir, regarding your talk in the chat window. So
I'll look later. Thank you.
yeah, sure, sir. And also, as the last question, like we can give you one chance to one person to ask just one more question.
Professor A.P.D. Silva.
Hello.
I am Mano Devi. Yeah, I am Mano Devi. Actually, I just
You are very welcome, Manodini.
Manava Devi.
Manava Devi, the boss herself. Thank you very much for joining us.
Yeah, I'm really sorry. At the beginning, I couldn't join. The thing was that I had an emergency. Now also, I'm in the hospital, but I wanted to just say thank you for you for accepting our invitation and then just giving us a very inspirational talk. So, so that's really nice to see you. If I show you my face, you see that I am wearing the mask.
Okay. Okay.
I'm in the hospital
Take
now.
very good care. Yes.
Yeah. So then thank you again for just giving us this inspirational talk. And somehow I just managed to listen to you. So it was
thank you.
really interesting. Yeah.
Yes.
So nice to
I
see you
hope
too.
everything works out fine now, because health emergencies are like one of the things I mentioned in the talk also was sometimes in chemistry we can help health monitoring. So I hope some of those techniques of science will help your family members now.
Thank you very much for the best wishes.
Yeah.
Okay, thank you.
Thank you.
There was a chance to ask last question, so I had a few questions.
Okay.
Nowadays, actually, people are looking for small and smaller gadgets, sensors, right? So miniaturization. So in that case, right? So if you try to use lower wavelengths, lower wavelength, high energies. So you might be able to go for smaller features, isn't it?
Yes.
So that you can draw, like, say, for example, you use near UV. If you go to deep or extreme UV, with argon fluoride or those sensors.
Yes. Yeah, as you know, like those 3 nanometer chips now, Those are drawn with X-ray. Yeah.
X-rays,
you're
yeah.
very right. Yeah, 3 nanometer features.
Accelerated electrons and accelerated
Yes.
ion beams.
Yeah. I suppose you are very right, Gamini. I think that is how I suppose the silicon people will drive down the size, and now they are nearly at molecular sizes. So 3 nanometer is now, I think Samsung now seem to say that they can put that into a phone. So 3 nanometer, and most of our molecules are like 1 nanometer. So they are very close now. But the big difficulty, I think, for the entire semiconductor community seems to be getting semiconductor devices into living cells. The living cell, because again, like wireless, then you have to put the antenna, and the antenna tends to be too big. So they can't put the device inside, even if it's 3 nanometer. So there seems to be a physics limitation. And so with molecules, we have no trouble. So I think a lot of new twist in molecular logic is intracellular computation. So like the first paper of that came out in Science in about 2010. So that was from Caltech. And so I think because the molecule is able to happily live there, and as you say, like if the lower energy wavelengths won't harm the cell, so with the molecule, then we don't have to cut features. So the molecular systems are very successful, it seems, so far in working in a living system, and in the future, hopefully, to intervene. So the silicon has that difficulty. As you know, implants, even large implants in the body, after a while, the body starts to reject it because So I think that difficulty still, I think, remains. But the size problem has been overcome very dramatically. So you're very right, Gavini.
So that, of course, rejection also, I mean, you can fool the body by making, like, I mean, put in some similar cells or something.
Correct. So like one of the things they try now is to cover the device, the silicon device, in hydrogel, and then to implant it, for example. So I think large scale devices, there's a potential to at least cover it with something. So then if you want to do single cell work, that of course is difficult because the cell is so small. So
what I am interested is AP, I want to put it on the skin and do sensing inside.
Sure.
Is it possible, something like that?
Oh, yeah. Because, for example, there are also some developments now, again, like one of my colleagues here does that, they use these micro needle arrays. So it's actually cut with a photoacid generator. You cut a silicon wafer, basically, but you cut it into small needles, and the needles are only about 1 millimeter tall, 1 millimeter, but the aspect ratio is very high. So you have to cut it very carefully. Like in all of Ireland, there is only one lab which can do that. So our friends have to send the dimension plan, and then they cut it and send it over.
Machine cutting.
Machine. Yeah. So then you put it on the skin, and then of course it goes into the skin because of the high aspect ratio. And then a little bit of the interstitial fluid, not the blood, because the blood capillaries even are too narrow. So you go into the fluid area. So you have to go below the dead cells, and then you collect a little of the fluid. So then you have to make assumptions. Then you have to make the assumption that the blood is equilibrating with the interstitial fluid. So that assumption is normally not true. So then they can't correlate very well. But otherwise, you can make those needles to be hollow, for example. Then the fluid will come into like a small tube, and then you can have a sensor inside. So there is some progress to do that. And they say it doesn't hurt. You just put it onto the skin because the aspect ratio is so high, you go between the nerve endings. So it seems nice. Yeah, but there is a big difficulty of this no equilibrium with the blood. And in fact, with Roche, we discussed that for doing detections through the tears. So at the moment in our Roche chip, you have to bleed the person. So it has to be a nurse or a pharmacist who has to take the blood. So it can't be done at home. But so they tried tears, like for glucose, for example. But then the tear sugar concentration and the blood sugar isn't always correlated. It correlates sometimes, then depending on body conditions, it changes. So there are still difficulties in the physiology, it seems. But otherwise, the impedance seems
that came into my mind because when I was at Imperial College doing PhD in 1980s, actually my professor had this physiology department as well. So he's
sure. Great.
Professor John Albury.
Aye, famous guy.
Professor John Albury had this enzyme electrochemistry group.
Exactly.
We developed glucose sensor, measure glucose level on the skin. And then we calculate glucose level in blood by considering the diffusion of glucose from blood to skin. So that diffusion equation can be solved easily. So
but the problem,
similar things we can do, isn't it? So something like diffusion or something.
Yeah, generally it's correct. But the problem, Gamini, if I understand is when you solve the diffusion equation, the starting conditions are sometimes not so clear. Like, for example, if the person sweats harder just before the detection, then the condition changes. The slopes of the concentrations change, for example. So in Roche, for example, they gave up the eye glucose project. Even though they had so much money and so much technical resources, they abandoned the program. And they just said, we'll just do ex situ blood. And so now a chip will have a glucose option, for example. Yeah. So even though doing it without bleeding is a huge advance. So I think people will struggle with it for some time with smartphone apps. And so they will continue to try, I think.
Right.
But the physiology seems to be the problem.
So we are late in about 15 minutes now. Sorry about that.
Sorry.
And, it's okay, sir. It's okay. We understand that. And I'm pretty sure that Rajapaksa is so much exciting about all this stuff. That's great. And also, there are some questions and then there are some comments in the chat window. And we already indicate your email address in the chat window.
Yes,
so,
please, people can write and I will slowly reply.
Yes. So we will definitely share all these things in the chat window with you through an email.
Please
and those who have questions can directly send to sir as well. So now it is over to Diniti.
Okay.
Thank you, sir.
Good evening. I, on behalf of the organizing committee of the INSPIRE and the Department of Chemistry of the University of Peradeniya, would like to extend a very hearty vote of thanks to Professor A.P. De Silva for adorning today's session with your outstanding research work and sharing with us your findings. Dear sir, you are an outstanding scientist with enormous contribution to the world of science. We are very appreciative of the knowledge you shared with us. Your incredible delivery on fluorescence sensing and logic systems would surely attract our undergraduates to pursue higher studies in that field. Dear sir, thank you very much for taking time out of your busy schedule to attend this event. I also wish to express my gratitude to Professor Chandani Pereira for inviting Professor A.P. De Silva to inspire and hosting him today. Thank you, Madam, for your encouragement to make this event a success. We appreciate the continuous guidance of Professor Manava Devi Ganehenage, the head of the Department of Chemistry, throughout the webinar series. Especially, I would like to thank all of you who joined us on Zoom today. Thank you for your active participation. I hope you all found this session fruitful and enjoyed listening to it as much as we did. Before winding up today's session, I would like to take this opportunity to invite you all to our next webinar, which will be held on 5th of August 2021 at 7 p.m. The invited speaker for the next webinar will be Professor Neil P. Mancat from University of Illinois, Chicago, USA. And he will be talking about multimetallic catalysis in biology and synthesis. Once again, thank you everyone. I hope you will have a pleasant evening. Thank you.
Thank you.